clearly? The slide?
It's still loading. Oh, yes.
Okay.
Now it's on.
Okay, perfect.
Time is yours, Professor.
Yes, thank you. If you cannot see the slide or lost something, please let me know. So, selamat pagi.
Selamat pagi, Prof.
Yes. So our course, computational chemistry. This is the continuing from last time. We will focus on the basis set. Okay, and I would like to say that this lecture today, probably you may have to step by step, think a little bit, probably quite some mathematics and functions behind. Okay, we will focus on the type of the functions, especially the basis function for molecular orbital, and also we will study about the development to make these mathematic functions more precisely and be able to apply to the molecular orbitals. And then we will like to see about the specific feature of the basis set. Okay, some kind of this. And today lecture and another 2 weeks, we will focus on what kind of we call ab initio quantum chemistry methods. But before we go to the ab initio itself, we need to know about the basis set. Because the basis set, I would like to say that it is the heart of quantum mechanics or computational calculations. So we need to know what is basis set, okay, and how many type of basis set that we use, especially nowadays. And for the post-Hartree-Fock and applications, which we will consider in the next 2 weeks, I think that you may have an idea about ab initio and its applications. And also, as some participants probably new for this course, I like to introduce that we will study in details about the semi-empirical quantum chemistry method and then density functional theory method at the end. Okay, this is our plan of the course. Before I go into details of the basis set, I would like to remind you a little bit about that actually quantum chemistry, it is very, how to say, quite almost 100 years of theory. And the main of the quantum chemistry is try to solve the Schrödinger equation, okay? However, this equation is very, very important, but it can solve only some simple systems. Some of you may remember about the modern physics and quantum mechanics. We can solve for the rigid rotor. We can solve harmonic oscillator and particle in the box. And for the molecules, we can only exactly solve the Schrödinger for hydrogen atoms. After the system contain at least 2 electrons in the atom, we need some kind of approximation, especially for the more complex system, like many electron atoms or molecules. Okay, some simplification, assumptions, approximations are needed to solve it numerically. However, we still possible to get the very accurate results as compared to the experimental data, as I mentioned earlier. Okay, so experiment work and also theoretical work, we have to go together. We have to support each other. However, the cost of the calculations, especially for the complex system, will be increasing. And also we expect to get the high accuracy. However, these two factors need to compensate to each other. Like if we have high computer or high performance computers, we can enlarge the system, okay? But for the prediction, the accuracy might not far, okay? So we need to come back to the method, to develop method, and then try to predict for the precise experimental data, confirm something, right? Some of you may remember this picture on the right-hand side. We have the length scale and then the predictability. Last week, I talked about the force field or molecular mechanics that we can be applied to the larger system like big molecules or biology. And right now we come to the smaller system, especially in the chemistry part, we look for accurate methods and the atoms may be not much, just 10 or 20. Or if we have high computer facilities, we can increase number of atoms. So we call it the ab initio, okay? And the ab initio will include Hartree-Fock, MP methods, and higher level of calculations. And later on, we have the FT and semi-empirical, which we will focus in the upcoming lectures, okay? So today, we are here. We try to study ab initio, okay? But before go to the ab initio, we need to know about the basis set, okay, or the basic function. So I like to use just a couple of slides to remind you our knowledge from quantum mechanics. We know that from quantum mechanics, when we try to solve the Schrödinger equation, there are three parts to solve the Schrödinger in molecular system. The first one is that we apply the Oppenheimer approximation. And this leads to the idea of potential energy surface, especially for diatomic molecules. Next, we still need some approximation. When we expand the many electron wave function, luckily, we have the Slater determinant to solve the many electron wave function, which sometimes include a spin function also, okay? And when we try to introduce or generate the many electron wave functions, there are so many methods, okay? And finally, the third approximation, which is very important, is that in order to represent the Slater determinant by molecular orbital, we need the linear combination of atomic like orbital functions, or we call it linear combination of atomic orbital to molecular orbital approximation, or in short, Lcaomo approximation. And in this approximation, then we need to know about the basis set. The basis set to represent the basis function of molecular orbital. So this is the key, okay? For today, we need to understand this first. And just for you who may not familiar with the Born-Oppenheimer approximation, this is very important approximation. Actually, this approach was proposed by Max Born and J. Robert Oppenheimer since 1927, okay, which is the early period of quantum mechanics. And I would like to say that the Born-Oppenheimer approximation is one of the basic concepts underlining the description of the quantum states of molecules. And it is the assumption that the wave function of atomic nuclei and electrons in molecule can be treated separately. This is based on the fact that the nuclei are much heavier than the electrons. You may remember that the nuclear mass of the nuclei is somehow about 1,800 times, okay, heavier than the electron. So in this concept, okay, von Oppenheimer approximation can be applied to separate the electronic properties of electron and nuclei. Okay, this is the first. And second, it is possible to separate the wave function of the electron and the nuclei, right? So there are so many details that I cannot go into details. Probably you have learned this in the fundamental of the quantum chemistry, or you can read more, okay, from this book. There are the electronic resources about quantum mechanics, many of them, and just try to study more if you are interested in. And next, the Slater determinant. For the Slater determinant, it is the function of the coordinate of number of electrons, if we call it n electrons, okay? So you can see that in the molecules, there are so many electrons in there. And so we need to construct the functions which represent all electrons in the system. And Slater determinant is help us. Okay, and this is the original of the Slater determinant. Okay, just the psi equal to normalized factor and Slater determinant of the atomic orbital of electron 1, electron 2, and etc. Okay, so this is a symbol that represent the orthonormal one electron function. Okay, and also sometimes we can include the spin orbitals. In order to solve the Schrödinger equation for the smaller system, we can do it. Okay, but for many electrons, so we need some kind of mathematical method to solve the Schrödinger, to solve the Slater determinant. But anyway, at the end, we can solve it and propose some kind of molecular orbital, okay, for atomic orbital, for linear combination of atomic orbital to molecular orbital. Okay, so based on this kind of Slater determinant, then the linear combination of atomic orbitals can be proposed in order to construct the molecular orbital. As I said earlier, this is the Lcaomo approximation, which is the main part of our lecture today. We will focus on Lcaomo approximation. So the initial assumption is that number of molecular orbitals is equal to number of atomic orbitals, which is included in the linear expansion. So in the sense, if we have n atomic orbital combined to form n molecular orbitals, which can be number I equal to 1 up to n, and then these may not all to be the same, okay? And the most important is that the expression, the linear expression for the I molecular orbital can be expressed like the equation in the screen. If you look, you have molecular orbital phi I equal to coefficient multiply with the atomic orbital 1 and do like this linear combination of atomic orbital. And then we can write it in short. Phi I equal to summation of coefficient multiplied by atomic orbital. Okay, chi R. This is the concept. Okay, so linear combination of atomic orbital to construct molecular orbital. Okay, this is the idea of Lcaomo approximation. And after this, we will look how to consider the atomic orbital, how to construct the molecular orbital, which we need to understand the basis set, okay? Or we need to understand type of basis functions. This is just remind about the history of quantum mechanics a little bit, okay? So now, I would like to say that this lecture, the expected learning outcome is that at least the audience, the participants or the students can know about the basis set. What is the basis set? Okay. And how many type of basis sets? And I would like to say that if you look in the textbook or the lecture materials available about the basis set, some authors or some writers may classify basis set in different way, okay, in many types differently, but you can understand whatever, okay, just start from the smaller to the more simple and then more complicated step by step. And at the end, you will know that basis set, there are some kind of types, important types of basis sets. So now I like to bring you to the focus on the basis set which used in molecular orbital calculations. Okay, Lcaomo. Okay, now molecular orbital calculations. Why do we need molecular orbital calculations? We need molecular orbital calculations because molecular orbital is the place that the electron occupy. Okay, so imagine the molecules, electron in the molecules, they can be very active due to electron delocalized. Okay, and then molecular interaction occur, chemical bonding occur, or chemical reaction occurs. So molecular orbital is then the heart of computational chemistry. If we get the molecular orbital very precisely, very good, very predictive, then the properties from computational calculations will be very precise, and then we can use it to predict whatever we are interested in, as I mentioned in the first lecture that I taught. Okay, so now we can see that each molecular orbital, okay, molecular orbital or one electron function, we represent it by psi, is expressed as a linear combination of n basis function. Psi nu, phi nu, okay. And this statement, again, I like to mention that it is the Lcaomo approximation. Linear combination of atomic orbital to construct the molecular orbital. Okay. So by convention, molecular orbital are abbreviated by the Greek letter psi. Okay, this is psi. While the basis functions are symbolized by the Greek letter phi. Okay, big phi like this. And then we use the equation 1 to represent molecular orbital is the linear combination of atomic orbital. And the C over here, it is the coefficients, okay, or the values that we can find out later on. We call it molecular orbital expansion coefficients, or simply molecular orbital coefficient, okay. And usually the basis function are located at the center of atoms and are therefore often called atomic basis function. Okay. Anyway, it is not strictly true, or in order to avoid confusion, we use basis function in general, right? So we call it basis function. So now this equation 1 is very important. This is the concept. Okay, Lcaomo is very important for computational chemistry. And from now on, even we talk about ab initio, Hartree-Fock, DFT, or semi-empirical, it will be based on Lcaomo approximation. Okay, but it will be something developed later to make the prediction of the calculation precisely and better, but starting from Lcao. So then, may I give you the scope of our lecture today? Okay, we will study on the basis function. What is a basis function? It is just a mathematical function that can be used to construct molecular orbitals. And we can use any mathematical function. There are so many choice, many ways. Okay, at the end, we need to get the molecular orbitals. Anyway, even if you remember my talk earlier, I showed to you about the very earlier state of quantum mechanics. There are not much research work come out, but just after 1980 something, computer provided technology and the development on molecular mechanics and how to solve the Schrödinger equation is increasing. Okay. Anyway, there are only few solutions which have found spreadly applications. Following, you can see that the type of basis function, there are about seven types that I would like to talk today. The first one is Slater type orbital, or STO. I need to ask you to remember a little bit about this technical term, because I will, or the lecturer will call it many times after that, after we learn about Hartree-Fock and DFT and semi-empirical. Okay, so we may learn about Slater type orbitals, which is the very classic one, very simple one. Okay, however, there are some problem about the try to solve the equation. Then the Gaussian type orbital was developed to solve the problem and make it more efficient. Okay, so we have the Gaussian type orbitals, or GTOs. Anyway, both STO and GTO somehow still have some problems and takes quite long time solve the equation. Then the third basis function type, which is the contracted Gaussian type orbitals, or I call it in short CGTOs, was introduced. And when even it's quite good and very acceptable, and we will talk a lot about the contract Gaussian type orbitals in this lecture. But later on, there are still have some development in order to put the possibility of for the electrons to be polarized, okay, and make the double zeta basis set, which we will learn next, okay. And later on, not only polarization, but also the diffuse basis functions was introduced to the basis set, okay. And more importantly, there are also the basis set for correlated methods, which is very high and very complicated level of theory. And at last, we will learn a little bit about the correlation consistent basis set. Okay, so I expect that the first, the second, and the third, these are quite important for us to understand, and then we can consider how the basis function can be polarization, addition, and diffusion, and so on. Okay. Next, probably I can introduce first to you the Slater type orbitals, or STO. I'm not sure any of you have ever heard about the STO. I hope that some students may know about this, okay, but not all, I'm sure. So for the STO, actually it is a function that construct from the radial part. Okay, the radial part. I like to tell you that for the basis function, actually it refer to the wave function in classical mechanics. Okay, and the wave function consists of two parts. There are two parts, okay? The first one is radial part, and another one is angular part. Radial part and angular part. And therefore, the equation 2 is the representative of the STO Slater type orbital, which you can see that it is the radial part. The so-called radial part means that the function depends on the distance, the radial of the electron from the nucleus, okay, and the n is the normalized factor, the constant normalized factor, which is also have some properties, very important one. And the YLM over here is the angular part. If I explain to you, the radial part consists of r power n minus n multiplied with the exponential of minus zeta r. Okay, this is the first part. Depends on the distance r from the origin of the basis function. Usually, it is the location of the nucleus. And for the orbital exponent zeta, this responsible for the size of the orbital. Okay, the zeta represent for the size of the orbital. Okay, and the n, it represents the principal quantum number. If you still remember, each electron has the quantum number n, l, m, and s. Okay, so the n over here means the principal quantum number. Why the spherical part, which stand by YLM over here, depends on the angular quantum number L, okay, and the magnetic quantum number M, right? And finally, the normalization constant. This is quite special because the normalization is chosen, whatever it is, but it should serve the integral over the square of the basis function, use unity. Okay, we call it normalization or orthogonal. Okay, this is something behind. Some of you who study about the modern physics and quantum chemistry may familiar with this principle. Okay, so Slater type orbital is simple, very, very simple and important as the first basis function that we consider. And if we consider, for example, the 1s orbital, some of you may remember that electron will be occupied in the orbital, okay, and the 1s is the sphere shape, right? Very simple. So the spherical part as well as the radial part equate to unity. And after evaluating the normalization constant, we can develop the STO type basis function as following in the equation 3. Okay, this is an example of the atomic orbital of the basis function of the 1s orbital. Phi 1s equal to, this is the normalization factor, and multiplied by exponential of the zeta r minus zeta r. This is an example, okay? And for the zeta, the physical meaning of zeta is very important because it controls the width of the orbital, okay? Larger zeta gives tight function, and smaller zeta gives diffuse function. Okay, so it's quite important. If you look at the picture on the right hand side, you can see that this is an example of STO function. When we vary the radius of the electron, okay, to be different value of zeta, like we have the exponential minus 0.2 r, minus 0.4 r in the pink, and minus 0.6 r in the orange, and exponential minus 0.8 in green. Okay, you can see that bigger, large zeta gives tight function. Okay, so you can see from the shape of the function, right? So you can have some feeling about the equation. Okay, how to get this equation is not easy, but if we get it, then physical meaning of the function, what does it mean? It depends on the zeta and also from the vector over here, the exponential part actually. So you can see the exponential curve over here, and the curve is different. Okay, depends on the exponential value over here. So in this plot, these are the hydrogen atom-like. Okay, just one electron. Hydrogen atom-like is the one electron, at least for 1s orbital. However, this kind of function lack gradient nodes. You may remember the orbital, they need the nodes, but 1s, there is no node. Okay, and therefore these are not pure spherical harmonics. Okay, for example, how can get the 2s or 2p and so on. Therefore, STO3G still need some correction, especially for the short range and the long range behavior. Okay, so we can say that Slater types orbitals are not very useful for electronic structure calculations because two electron integrals over SCO are difficult to calculate. This is the limitation of this basis function. Now, in order to cope with this problem of the STO, then the Gaussian type orbital or GTOs was introduced. And the GTO itself are constructed from a radial and a spherical part, the same as STO, okay? But the radial part has a different dependence on the radius. Equation 4 show to you about the Gaussian orbital. So this is a function equal to n, which is still the normalized section, and the term exponential of minus alpha r squared, okay, multiply with the x, y, and z, and z, the z, okay. So I will explain to you. You need to a little bit understand about the radial part and the angular part. But in the the GTO function, the radial extends to proportional to exponential minus alpha r squared. This is very important. You need to look at this, minus alpha r squared. The alpha being the exponent, any value, okay? And the normalization constant n still serves a similar purpose as for we consider from the STO. That means the normalization should be the integral part of the normalization should give the equal to 1. And the spherical part is now expressed through the Cartesian coordinate. The spherical part right now expressed through the Cartesian coordinate x, y, and z in powers of a, b, and c respectively. Okay, and for the exponent a, b, and c, please should not be confused with the quantum number. Yeah, it's different. And then may I continue to explain to you about the Gaussian type orbitals. For the details, the sum of these exponent L equal to a plus b and plus c. This exponent is used to define the angular momentum of the basis 3 function. For example, if we consider S-type, L equal to 0, P-type, L equal to 1, D-type, L equal to 2, and F and G, etc. Okay. And for the simple Gaussian function, which is represent the 1s type orbital, resulting in the basis function as shown in equation 5. Quite similar to equation 4, but the difference is that the Gaussian function equal to the normalization factor over here, multiply with the exponential power minus alpha r squared. R squared is very important. If you look on the right hand side, this picture shows the Gaussian type orbital. And the exponential, for example, minus 0.2 r, minus in blue, and minus 0.4 R in pink, 0.6 R in orange, and minus 0.8 R in green. You can see the difference, okay? If you consider this, okay, same thing, but this one is very tight, okay? But for the GTO, you can see the shape is quite nice, like Gaussian curve, like quite nice. And the most important is that in order to solve the function r square exponential minus r square, this one is more easier than the STO. Okay, this is the advancement of GTO type basis function. So the GTO are very useful for the electronic structure calculations because the two electron integrals over the GTO are not difficult to calculate. The reason behind is that exponential of r square, it is more easier to solve. Okay, if you remember when you study the differential equation or something, okay, r square is more easier. This is the good thing of GTO. And for the GTO, another advantage is that all the integrals needed for the LCAO calculations can be done by using simple formulae. Yeah? So at this point, I would like to say that GTO is good in terms of easy to solve the integrals, not take so long time, right? So you may interested in seeing the comparison between the STO and the GTO. So there are two major differences. Okay. The first one is that we have to look at the behavior of the function for the R, the radius equal to 0. That means at the nucleus. How about the function? And when the radius is infinity, very far away from the nucleus, what is the behavior? So from this curve, if we compare the GTO and the STO, okay, exponential of the GTO is the minus 0.2 R square, and for the STO, the exponential of minus 0.2 R, okay, the same value, but you have R square for GTO and you have only R exponential for the STO. You can see that this is the curve of the STO, okay, the curve of the STO very tight. But for the GTO, it shows nice Gaussian type curve, okay? But when you look at the R square equal to 0 here, behavior for R square, behavior for R equal to 0. This means at the nucleus. The STO display occurs, okay, at R equal to 0, while the GTO has the incorrect behavior. You can see that incorrect behavior, okay, over here at the nucleus. And moreover, the GTO fall too quickly as electron gets further from the nucleus. That means if electron close to the nucleus, it shows incorrect behavior over here. But when we far away from the nucleus, it fall, the function fall too quickly, right? Anyway, what we have learned from this is that for the GTO, it's much easier to compute, Okay, and this is very convenient, and most of the quantum chemists like to use GTO rather than STO because it's more faster, calculate more faster. So now you know about two basis function, STO and GTO. I will go a little bit further to the third type of basis function. We call it contracted Gaussian type orbital. Okay, because there is a problem about the STO, which actually it is more accurate than the GTO, but it takes longer to compute the integrals. And the solution for this is that we need to use a linear combination of enough GTOs to mimic an STO. Okay, that means we can use small things combined together in order to represent the big one, okay, or the real one. For example, we like to have the STO because it's more accurate, but takes time. So then the combination of Gaussians in Gaussian functions to mimic an STO is often called an STONG basis. Okay, even though it is made of a contracted Gaussian type orbital. I mean, actually the contracted Gaussian type orbital is the one of the type of the basis function, but most of the people call it in the term STONG because it's famous, okay, but actually it's the same. And for the graph on the right hand side, this is the meaning of the combination of Gaussian in Gaussian to 1 STG. For example, if you look, the curve in the black line, you remember that this is the STO or the Slater type orbital. You can have the very tight function over here. And we said that STO is very hard to solve the integrals. It takes so long time to finish solve the problem, solve the integral. It's not convenient. Then if we use one Gaussian in the small dot over here, you can see that the function of one Gaussian is not perfect. It's not perfect because it looks like perfect over this part, but the radius close to the nucleus still be far from the complete function that should come to this, right? And then if we have two Gaussian STO2G, that means combination of two GTO to represent the one STO. Here is the curve. It improved more or less, okay? It improved more or less, covering this part, okay? And also close to the nucleus, but still there are some gap over here. Then the next is the STO3G. The combination of 3 GTO represent 1 STO. You can see that now the function is improved to represent close to the nucleus and close to the STO. And again, for the falling of the curve is still quite nice. So I would like to say that the contracted Gaussian type orbital, in this way, most of the quantum chemists they use STO3G. Okay, that means we need to use the linear combination of Gaussian type orbital, three terms to represent one STO function. Okay, and the general equation of the basis function of the CGTO can be represented in this equation 6. Okay, you can have the normalization factor and some coefficient and multiply with the x, y, z, which is the Cartesian coordinate, and the radial part still exponential of minus theta r square. Okay, so this is quite nice, quite nice. So if you know about the Cartesian coordinate, you know about the coefficient, and then you know about the normalization factor, you can have the complete equation, right? So if you interested in, you can learn more about the SCONG. So I think, Mita, may I ask to take a quick break for 5 minutes?
Sure, Prof.
Yes. And
Sure,
during
sure.
this time, if the participant, the audience, if you have some question, please let me know, or you can send from the chat. Is that okay?
Yeah, sure, Prof.
Yes.
Yeah.
Because from now on it's quite a little bit complicated. So I think we should take a break. And
Yeah,
then we
sure.
can discuss more. Thank you.
I like that idea.
Yeah. Okay, see you about 5 minutes. Thank you.
Okay, thank you.
Yes, thank you, Professor.
I will stop sharing.
Hi, Prof. Supa.
Hi, welcome back.
So we can start again, but I
Yes.
guess there is a questions in the chat box.
Yeah.
Should we talk about this or we continue our meeting first?
Yes, we can do it. Yeah.
The questions is from Yasmin. There are so many type of okay.
Many type of basis set that we can choose how to choose the right and accurate basis set for the research. And we are going to do, please advise or tip to choose the right and accurate of basis set. Okay. Actually, this question is very good. And when we use the methods like ab initio, DFT, or semi-empirical, okay, we need to select the basis set in order to make the appropriate to our system. For example, if your system is not large, just some molecule, just some atoms, like 10 atoms, you can apply ab initio, okay? And then you can select, for example, SCO3G as minimum. SCO3G is minimum, okay? And then you can select higher, I can say higher basis set or higher method of calculations if you have capacity of computing facilities. Because if you apply the higher level of theory or basis set, you need longer CPU times, okay? Sometimes it's not convenient, okay? So you have to consider your system and level of theory, okay? This is the reason. And if you play with organic molecules, sometimes 631G is good. 631G is good. You can apply higher calculations, no problem. But if your system combined with some metal ion or something, yeah, you need higher or very specific basis set. Okay. So my answer is that it depends on your system. And you can try as best as you could do. But for me, if we have the system that nobody ever calculate before, we need to compare about the results between the minimum level of theory to the higher and see about the computing times. Sometimes you even put the very high level of theory, but the result is not different from lower level of theory, okay? So we will select the lower level of theory because need not to be higher something, okay? So, and it depends on your method, ab initio or DFT. If you use DFT, you need to select some level of theory. If you use a small level of theory or lower level of theory, sometimes it's not good, right? Okay, so for the advice or tips, we will talk later, okay? After this, yeah, we will discuss how to select. Thank you.
Okay.
So then we can continue.
Yeah, sure, we can continue.
Yes, so this is slide number 17. You have seen correctly. Minimum basis set. Is that okay, Mita?
Yeah, sure, Prof.
Thanks. Now we still in the contracted Gaussian type orbital or CGTO And in short, we call it STONG, okay? And very famous method is that STO3G. When I was the graduate student, I used STO3G, but now not. I use higher because the computer is providing opportunities to apply by the higher level of theory, okay? So we need to be higher as best as we could do. And the minimal basis set, look, this is, the term is already defined clearly, minimal basis set. It is the single Gaussian function as described earlier in equation 4, okay? So Mita, after finish this lecture, I will send you this handout material, okay?
Thank you, Prof.
Sorry that earlier I could not send, but after finish, I will send you immediately, and then you can send to the student. As I mentioned earlier, the GTO are not well suited to describe the spatial, expand, and the nodal characteristic of atomic orbitals. And to solve this problem, the basis function are described as a sum, or another term, contraction of several Gaussian functions, which we will refer to the primitives. Equation 6 is very important. Yeah. So you need to highlight this equation 6. It is the Gaussian functions. Sometimes I call it the primitives function. Yeah? And for example, carbon 1s orbital. How to get the STO3G. So from this curve, you can see that combination between term 1, term 2, and term 3. Okay, each term, this one is the exponential, yeah, exponential part in the Gaussian function, if you remember. Yeah, you can have separate function, D1G1 function, D2G2 function, and D3G3 function. Each function are not perfect, right? But if we combine all three functions, then we can have the summation of the function over here and show very nicely Gaussian curve. Okay, this is represent the carbon 1s orbital by the STO3G function. So now we obtain a very nice basis function for 1s orbital. And then if we ask how many basis function do we need for a small organic molecule such as methane, CH4, okay? So we know that for each of the atomic 1s, 2s, and 2p orbital, the STO3G basis function use a contraction of 3 Gaussians. Okay, that means one orbital use one basis function. So in order to consider the methane, we have 1 carbon atom and 4 hydrogen atom. And for hydrogen atom, there is 1s orbital. Okay, that means we have 1s orbital, and then we have 4 basis functions. Sorry.
Sorry.
Hafiz,
help.
Yeah. I missed that.
Sorry.
I apologize.
Yes.
Apologize.
It's okay, no problem. And next, if we consider the carbon atom, you remember that carbon atom itself consists of one s orbital, two s orbital, and p orbitals, which there are 2px, 2py, and 2pz orbitals. And for carbon atoms, therefore, there are 5 basis functions. In total, for methane, you have 9 basis functions because one orbital need one basis function, right? Okay, and one basis function consists of 3 GTO, if you remember. And finally, for basis set STO3G, result altogether 27 primitives Gaussian function, right? So step by step, yeah. If you understand that we need one orbital, need one basis function, and one basis function, one SCO, you use 3 Gaussian. Therefore, methane has 9 orbital and 9 basis functions. And at the end, you can consider that methane consists of 27 primitive Gaussians. So if you remember, this is the primitive Gaussian. So you have 27 primitives Gaussian, okay? So this may a little bit, if you are already learned this before, then no, nothing, very easy, okay? But for the new learners, probably you step by step, okay? And I think the example of methane is nice to understand. You can think about methanol, for example. You can have methanol. Now, most of the quantum chemists accept SCO3G basis set. Okay, and how good of this basis set? In order to answer to this question, it depends on the chemical problem at hand. Okay, and the structural feature of the ground state molecules are reproduced quite often with quite good accuracy at the Hartree Fock by SCO3G level of theory. Okay, and for table number 1 here, it lists structural parameters of methanol as predicted by variety of theoretical method. So if we ask if SCO3G good enough, then you can see that for the methanol, yeah, the CS orbital, we have Hartree Fock SCO3G and several example of the basis set, which we will learn a little bit more in further, okay? But in this table, this is the minimal basis set, okay? And these are the higher level of theory, more accurate, more CPU times, and more providing polarizability, diffusion, set, and so on, okay? And even the MP2, yeah, which we will study next. The most important is here, experimental data. For the CO bond, yeah, experimental say 1.421. 1.421. And you see that SCO3G predict 1.43. Yeah, it's quite nice. Even we use higher level of theory, it just a little bit plus or minus, a little bit plus or minus. So why do we need to use higher level of theory? Yeah, sometimes it's not, because the small organic molecules, STO3G can be good predictive basis function already, okay? some simple, simple organic molecules. And if you look at the angle between the atom COH over here, experimental data 108, this is the angle. And the prediction by SiO3G is 103, and the others still plus or minus from 108. I think that this is acceptable because the experimental data, I guess, probably obtained from X-ray crystallography, okay? But for the calculations, it is done by the gas phase. Therefore, it is not possible to predict exactly 108. No. It should be somehow plus or minus, and the difference about 5 degree, I think it's acceptable, And this is the basis function. From the minimal basis set, SiO3G, there are 14, and other high level, they expand many of basis function and takes CPU time, computing time so long, right? So this example is that minimal basis set like SiO3G is good enough for small organic compounds, okay? It's clear. But if your compound is so sophisticated or complicated, you may need other method of calculations. And now for carbon atom SiO3G, what about the value of the basis function? This is the carbon atom C. And this is the result from program called Gaussian 94. Okay, when you calculate, try to computation, try to solve the integral, try to find the coefficient, try to find the normalization factor. At the end, you will obtain the basis set for 1s orbital. 1s orbital, you have 3 Gaussian type orbital, 1, 2, 3, combined together. Yeah, you remember the curve. Yeah, and for the orbital 2, you have 2s and 2p. You also have 3 Gaussian type. Okay, so these are the example of the basis set SiO3G. During the calculations, you will have some kind of this. So you cannot use solving by hand, okay? So we need computer to solve the integrals, and we will work on that, right? So if you have question, please chat or we can discuss. From the minimum basis set, now I bring you to a little bit another type of the contracted GTO, still in the section of contracted GTO. It is so-called split valence basis set, okay, in the group 1. And based on this group of basis set, I would like to say that the 321G basis set is very famous and very widely used, even now better than SiO3G. Okay, SiO3G is simple, very minimal. Yeah, right now we should start from 321G basis set. And what about the split valence basis set? So now look, still in the GTO, the description of the valence electrons. So I highlight the red color over here because we are now consider valence electrons. So all of you may remind about the electron that how many electrons in the atoms. It will fill in 1s first, 2 electron, and then 2s, 2 electron, and then 2p x, 2py, 2pz, okay, and fill in. And whatever electron in the outer layer, we call it valence electrons, right? So this is the point. We consider the valence electron, okay? And this behavior of the valence electron can improve significantly, yeah? If we add more than one basis function to the valence electron, okay? In the former, I told you that here, one orbital use one basis function, okay? This is clear. But now we consider if the valence electron can have more than one basis function, okay? The answer is yes. Now, continue. Valence electron can have more than one basis function, okay? Therefore, the basis set in this type are called split valence. Okay, that means the basis set as the description of valence electrons, valence orbitals are split into two or more basis functions. Okay, and it is another term which is quite famous, and sometimes it is the type of the basis set. We call it double zeta. Double zeta, probably you may remember the Greek symbol, the zeta, okay? The zeta exponential minus zeta r or minus zeta r square, okay? In the component of the STO or the GTO. And the term double zeta does not simplify because sometimes you have two basis functions and sometimes we can have more than two. So now double zeta continue for the split valence basis set, 3-to-1G basis set. Okay, I like to tell you that this is very famous and very popular basis set, especially for most of the organic molecules. If you would like to run the ab initio, you need to use at least 3-to-1G basis set. It's very economical, small split valence basis set. Okay, small split valence basis set is the 3-to-1G basis set. The non-valence electron, that means electron in the core, will be described by single basis function and composed of a contraction of 3 Gaussians. But for each valence electron, it will be described its mobility in the orbital by using 2 basis functions. Yeah? So this is very important key point. For the 2 basis functions, the first of the 2 is composed of 2 Gaussian primitives. Okay, 2 Gaussian primitives, while the second consists of a single uncontracted Gaussian primitives. If you still remember primitive, okay, so let me show to you an example, then you can understand clearly what about the 3-to-1G basis set. An example about the carbon atom, you remember that carbon atom consists of the orbitals, namely 1s, 2s, 2px, 2py, and 2pz. Okay. Right now, for the 3-to-1g basis set, each orbital consists of 2 basis functions. Okay. Each orbital consists of 2 basis functions, resulting in 1s, 1s prime, 2s, 2s prime, 2px, 2px prime, 2py, 2py prime, 2pz, and 2pz prime, right? So now we call it split valence basis function. I think you may try to understand step by step, okay, from SCO to GTO to contracted GTO, okay, to the SCO3G, and right now we introduce the 3-to-1G basis set, and we consider only valence electron that have 2 basis functions. Step by step. And then yeah, sorry. I think, no, sorry. I have to change this one, 6, 3, sorry. Yeah. Type 2. So then we have split valence basis set type 1, 3-to-1G. And right now, I like to introduce to you the split valence basis set type 2, which also very famous 631G. If you have computer facilities, quite high performance, you can apply 631G basis set. Nowadays, it's very popular. Yeah? Because the scientists, the quantum scientists who develop the method, they try to introduce many types of mathematical functions in order to improve the predictive ability of the 3-to-1G. Now, the split valence basis set type 2, we call it 631G basis set. Okay. Actually, the scientists, they try to apply 431G, but the result is like not much improved. And at the end, the 631G split variance quite improved as compared to the 3-to-1G. And so when we consider the main difference between 3-to-1G and 631G is that a much larger number of primitives is used in the latter 631G, especially in the core as well as in the innermost valence shell. So if you have the molecules, for example, methanol or methane, you can compare the calculations by using 3-to-1G and 631G. The difference will be the CPU time, that very long time solving the integral part. Yeah. Because so many primitives in the core orbital. And the use of the contraction of 6 Gaussian primitives for each core orbital improve the description of the core region significantly. This is quite important. It improves the results. And also, the valence region is again described by 2 basis functions per atomic orbital. Okay, and the inner shell is composed of the contraction of Gaussians, and the outer shell consists of 1 single Gaussian primitive. Right? The most important that I would like to mention is that this kind of split valence basis function, 3-to-1G or 631G, these were developed by Professor Popo, okay? And we call sometimes Popo basis set, the Popo basis function. And the S and P function share the common components, yeah, very famous. So look at this example again to make you a little bit clearly on that. The split valence, again, I have to change this. 31G, sorry for that. Yeah. For example, if we consider carbon atom, again, orbital 1s, 2s, 2px, 2py, and 2pc. 1s is the core orbital, right? You remember that? This one is the core orbital. So it has one basis function, okay? One basis function means there are 6 primitive GTO, yeah? 6 primitive GTO. And for 2s, 2px, 2py, and 2pc, these are considered to be outer orbitals. And therefore, outer orbitals will have 2 basis functions, 2 basis functions. The first one consists of 3 primitive functions, and another one is 1 primitive function. Okay, so the Popo style basis set is very, very common and famous, and therefore, if you look, Professor John Popo, who won the Nobel Prize in Chemistry for his breakthrough in quantum chemistry, 1998. Okay, notation 6 means 6 primitive contracted to a single contracted Gaussian, okay, to describe the inner, the core electrons. For example, 1s, okay, in atomic carbon. And for the letter 1G over here, that means they use 2 functions to describe the valence orbitals. In this case, it is the 2s, 2p, and 2s and 2p in atomic carbon. And one is the contracted Gaussian composed of 3 primitives. And the second is a single primitive. Okay. So you may have to remind to the primitives. You can have 1 primitives, 2 and 3 primitives, linear combination, okay, to be 1 basis function, right? So in this case, I would like to mention that Popo basis set, okay, as developed, as I said, and SCO3G is a minimal basis set in which each atomic orbital is represented by 3 Gaussians, 3G, chosen to mimic the behavior of the STO, okay? And Popo split valence double zeta basis set is called 631G. The core orbital is a CGTO made of 6 Gaussians, and the valence is described by 2 orbitals. 1 GTO made of 3 Gaussian and 1 single Gaussian. Okay, I just like to remind a little bit message. Yeah, so now probably you can understand about the difference between the minimal basis set and the split valence double zeta basis set. Okay, not only the double zeta, sometimes you can have 3 basis function for each atomic orbital. Now you know about the split valence basis function, basis set, and the double zeta. That means we have 2 size of basis functions for each valence atomic orbital. Right, in the hydrogen atom, we have 3 to 1G. In methane hydrogen atom, you have 1S and 1S prime. For carbon atom, you have like present here. Okay, this is the double zeta. For valence electron, you have 2 basis function. And for the triple zeta, now you can have 3 size of basis functions for each valence atomic orbital. Okay, in this case, the methane, you can have hydrogen atom, they have triple zeta. Okay, that means you have 3 basis function to represent the valence electron. Okay, and for the carbon atom also. And now the basis function per atom in the notation of split valence basis set between 3 to 1G, this is the double zeta, and the 6311G, this is the triple zeta. Okay, so now you can have this kind of split valence basis set. Just remind you to remember that if you use 631G, okay, you will have many of the primitive functions in the core electrons. So you need high performance computer to solve the integrals. That is only the limitation. Okay, if you cannot have the high performance, then you can use double zeta for good predictive ability, right? So the question in the chat before this, yeah, after the break. So now you can consider that your system first and your expectation to have, yeah, and also your computing facilities to make your selection of the method. For me, I love 3 to 1G at least. And right now, because the computer time, the computer facility is better, then I can use triple zeta. Yeah. And here is the example of 631G for carbon atom. Okay, so you can have that 1s orbital of carbon atom. You can have 1, 2, 3, 4, 5, 6 primitive function, and this is the zeta. Okay, and this is the R, the term in the primitive function, and here is the 2s, okay, and 2p, and also you can have 2s and 2p, 2 basis function to represent 1 orbital. That means the first you have 3 primitive function, and another one you just have 1 primitive function. Okay, so imagine just only carbon atom. If you have methane, if you have benzene, if you have naphthalene, okay, so a lot of computer time to solve the integral part. Now a little bit, just a little bit further to the contracted GTO type 4. We call it double zeta basis set, which introduced by Dunning, okay, and very famous, the 95 basis set. Just to introduce to you a little bit, the 95 basis set is a full double zeta basis set. Full double zeta basis set. In that, it allocates 2 basis functions for each atomic orbital of the core. Okay, and as well as the valence region occupied in the electronic ground state. Double zeta and the triple zeta, we allow valence electron to have 2 basis function and 3 basis function, but the Dunning D95, they allow all orbital, even in the core, to have full double zeta. So you can imagine that this is the carbon atom, and therefore you can have every orbital, yeah, very complicated and very huge amount of integral to be solved. And this one mainly describe one core electron carbon here, only core carbon. Okay, and here is the 2s valence orbital. But I don't want to make you uncomfortable with many of numericals like this. Nah? Don't worry, just know about types. Okay, and in the future, if you need to work on selection of the basis set, you can come to the details and try to find the most suitable for your system. Okay, so the basis set type 3, I introduced to you 4 subtypes. Okay, now come to the next quite interesting. The basis set type, the type 4, we call it polarization functions for double zeta basis sets. Okay, still use double zeta basis set. In this case, as other atom approach and atom orbital might want to shift, okay, atom orbitals might want to shift to one side or polarization. You may remember electron. For example, in water molecules, we have oxygen and 2 hydrogen atoms. The electron not located in only center of the nucleus, I mean oxygen atom, but sometimes it can interact and go into the whole molecules. Sometimes we need the orbital that allow electron to go out from their valence shell. Okay. For example, an s orbital can polarize in one direction if it mixes with a p orbital. Okay. So electron does not stand only in s orbital, which is the spherical, but it can polarize a little bit further to one direction to the p orbital that match to its direction. And also the p orbital can polarize, okay, if it mixes with the d orbital. Therefore, in general, to polarize a basis function with angular momentum L, mix it with the basis function of angular momentum L plus 1. So this gives the polarized double zeta or double zeta plus polarization basis sets. Okay, this is the concept, right? So if you look in this picture, you can see that this is a 1s orbital. Okay, 1s orbital, it can, electron in 1s can a little bit polarize to one direction to combine with the p orbital. And then you can have some kind of this orbital like this. This is the shape of the orbital that electron can stay in. The same if you have the p orbital and d orbital like this. Okay, so electron can polarize to one direction and then it can stay here in the orbital. So in order to allow orbital, it changed the shape. Okay, add p orbital to hydrogen atom, add d orbitals to second row atoms. You remember in the character in the periodic table, yeah, the second row atom. Or we can add the f orbital to the transition metals. Okay, so if you deal with transition metal, you need to use the basis set that allow the polarizability of the orbitals. Okay, but if you have only organic molecules, you need not to use polarization. Or sometimes if you have the aromaticity in the molecules to happen the reaction, so you need the polarization. Okay, it depends on the system. And right now, the basis function will be introduced into this formula. For example, we have the double zeta basis set, sig31G. Okay, we have sig31G, we studied earlier. Now, we add the term polarization by add bracket and D, like this. That means D functions per heavy atoms. D function per heavy atoms. And sometimes the symbol of this basis set, they use sig31G star. Star means polarization per heavy atom. Okay, per heavy atom. Okay, this is the keyword. And if you have sig31G dp, that means you allow the function to overlap in the D function per heavy atoms, and also the P function to hydrogen atoms. That means now you will have bracket D and P, or you can have denoted as sig31G double star. The first star is the D function polarization per heavy atom, and the second star means polarization on the hydrogen atom, P function, right? So now it is quite nice, sig31G star or sig31G double star. I would like to say again, if you have computer time that high performance, you can use sig31G star and double star, okay? And here it is the example of the carbon atom of sig31GD for carbon atom. Yeah, you can see that you have 6 primitive for 1s orbital, and you have 2s and 2p. Okay, 2 set. Okay, 2 set. The first set you have 3 primitive, and the second set you have 1 primitives. And also you have the d orbital on the heavy atom that allow the electron to be here, right? Now I have to go a little bit further. Mita, how do you think? Yeah, still with us?
Sure, if you don't mind, we can continue.
Okay, yes. I think now I will go a little bit faster, because I think the first 3 type of basis function is important. Yeah, if you understand that, for the later set it will be okay. Now I will introduce to you the diffuse basis function, again for the split valence basis function. Okay, to reflect the addition of diffuse basis functions in all non-hydrogen atoms, a plus sign is added to the standard basis set notation. Okay, now you have the standard split valence 321G, 631G. Okay, you can add polarizability, polarized function, and then you can add diffuse function. Just add plus after the basis, the standard basis set. Okay, if diffuse S-type function, they are also added the basis set of hydrogen atoms. Okay, that means you need to put a second plus. Okay, and for example, using carbon, the combination of the 321G basis set with 1 set of diffuse SP function yields the improved this basis set 321 plus G. Okay, that means the first plus you allow the diffuse basis function to the non-hydrogen atoms, and if you add the second plus, that means you allow the diffuse function to both heavy atom and hydrogen atom. Okay, for more simple, just add diffuse function after the standard split 631G or 631G plus or 631G double plus. Okay. For the physical meaning of the diffuse function, you can see that the zeta term, this is the exponent term. This means the electron is held far away from the nucleus. If it's small, zeta, far away, okay? But if it bigger or larger, that means it's close to the nucleus. Yeah? Especially for the anions. In the Rydberg state, very electronegative atoms like fluorine with a lot of electron density. In this case, the necessary for accurate polarizability or binding energies of van der Waals complexes. Okay, because the van der Waals is the interaction that bound by dispersion, okay, by the interaction of the ion. So it is very bad to do computation on anions without using diffuse function. Your result could change completely. Okay, that means if you work with the anion, you need to put the diffuse basis function on the basis set. You need it. Okay, this is the advantage of diffuse function. And in this part, I just like to summarize again about the Opal basis function. You have 321G, you have 631G. Right now, in summary, you can have 631G star or 631GD. Okay, with you add the polarization on the non-hydrogen atoms, and double star if you plus polarization on hydrogen atom. Okay, and next you can have the triple zeta split valence if you add GTO to the 631G, and also you can add the polarization function to the heavy atom and to the hydrogen atoms. Okay, and so in the basis like 631G, the 3DF or 2PD, you can add 3 sets of D function and 1 function of F function to heavy atoms, and 2 sets of P function or 1 set of D function to hydrogen atoms. Yeah, this is quite complicated. Okay, but just introduce to you that you can do a lot if you know about the foundation of the basis set. Okay, you can select, okay, you can expand the polarizability, you can expand the diffuse ability to the basis function. In some case, you need to very specific like this, yeah, like this, but not common. Yeah. Now, I cannot see. The reflex of the addition of diffuse basis function on all non-hydrogen atom, a plus sign is added to standard basis function. Okay, and if diffuse S function to hydrogen atom, then you put the second plus. For example, carbon as an example, you can have the standard split valence basis set like 321G. Okay, and if you one set diffuse SP function, you can improve the results as 321G plus. Okay, so in this case, 3 and 2, 1 plus basis set. Yeah, this is the example of carbon atom. So now you can see the step by step. Okay, may I a little bit? I will finish by not so long, just 1, 2, 3 slide. I hope.
Okay, sure.
Yes.
Sure, Prof, it's okay.
Sorry. The basis set for correlated method, Gaussian child orbital. Okay, correlated method. I try to put some sentence because sometimes the student can read the slide and then you can learn more, okay, a little bit more. I like to introduce this because these basis sets are usually at least double zeta quality and also include polarization functions, okay. And one typical example is the 6311G 6311G DP basis set. The basis set consists of core region of 6 contracted Gaussian primitives. You may remember that. And triply split valence basis set using 3, 1, and 1 Gaussian primitives. For the polarization function on the first row elements consist of the set of 5 PLD functions, while the set of 3 p-type orbitals are added on the hydrogen. Okay. And in total, this yields 18 basis functions for each non-hydrogen atom of the first row and the 6 basis function for hydrogen. Okay, and the basis set for carbon and hydrogen can be present on the right hand side. Okay, so I just try to again introduce to you, okay, the correlated method Gaussian type. This is one group of the basis set. Yeah. So these are the details of the basis set for carbon atom. Okay, and these are the basis set for hydrogen atom. Now you can have not only one s orbital, but you can have some polarizability, okay, to the d orbital, to the d PLD function and the p, even p orbital for the hydrogen atom. So you can see that this type of basis set is really huge CPU time if you have to computation the system. Yeah. Let me introduce to you the last type of basis set. Okay, this is the correlation consistent basis set. And really advanced, I mean, not common, not common, quite advanced and very specific system that you will select the correlation constant. Okay, it is the series of basis set for correlation that developed by Dunning. Okay, and the basis set are referred to as the correlation consistent or CC, and are designed such that the basis set of SP functions is combined with correlation functions. The latter functions are chosen, such as all functions in the given set lead to a similar lowering the atomic correlation energy, or calculated by the CISD. The smallest member of this series, and thus often starting point of the correlation function, is the correlation consistent polarized double zeta basis set, decided as CCPVDZ. Okay, we will deal with this kind of correlation method in the next 2 weeks. Okay, so when we talk about the correlation method, we need to use this kind of basis set. The minimum is that CCPVDZ, but we can have higher, okay, like CCPVTZ or QZ or 5Z or 6Z. Yeah, and you can see this is the orbital that include in the system, and here is the basis function related to each correlation consistent function. Yeah, and I like to give you a little bit example that the component of the most diffuse basis function in the OCC-PV exact basis set have been optimized through Hartree-Fock and CISD calculations on the negatively charged atoms. Okay, this is very important because when you use the basis set that deal with the negative charge, it's not easy to solve in the integral or to solve in the calculations. And sometimes if you not include this kind of functions, you can get the result, how to say, incomplete, right? But if your system deal with the negative charge atoms, you need to use the CC or the OCC basis set. Yeah. Therefore, the basis set in this group is recommended to use with the positively or negatively charged system. Okay, and this table to present the proton affinities for hydrogen fluoride, and this calculated by the CCSD, very high level of theory. And if you use different basis set, you can obtain the different proton affinity. And the real experimental data is 122 kilocalories per mole. You can see that only the very high CC PV, yeah, can be close to the experimental one, right? If the lower is not bad, yeah. But if you like to have the very precise data, you need to very high level of basis set or theory, right? This nice example, I think. And also this one in terms of the energy, like the charge system that you use the OCC basis set of superior over the CC basis set. Yeah, if you use the charge, then you need the OC. Yeah, and when you like to have the complexation energies, for example, calculated in the system of water dimer, the data in the table 3 show to you the interaction energy of the water dimer. Yeah, based on the MP2, RIMP2 calculations. And these are the basis set. This is the CC, and this one is the OCC with the different theta. And you can have the interaction energy. And you can see that on the higher level of theory, OCC P5C show very close to the experiment. Okay, and the theory, actually the theory, the base of the theory reached minus 3.2, and the experimental is about 3.6. Okay, so you can see quite nice, and make us understand about the power or the efficient of the basis set. Okay, in your case, as I said, the system is important if you deal with the charge, positive charge or negative charge. You would need the correlation of function, right? So just this is the end of my talk, and just give to you about, if you search using keyword basis set on the Scopus, you can see the extremely increasing publications about calculations, and probably some application or development of the basis set also published elsewhere, and quite exciting research. Still, development of the basis set. So at the end, Mita and all, I think, I do hope that the student may try to understand what is basis set and how many types of the basis set. Okay, you can explain, you can read more from the books or from the online system, okay, information, and you can try to summarize on that. And it would be also nice if you can explain the applicable of each basis set. Sometimes there are some limitation on it, right? And sometimes very specific system and you need specific basis set. And I do hope that we will meet again next week, that we will work on the ab initio, Hartree Fock, MP2, and so on, right? And yeah, another 2 weeks, we will work together and see about the applications. Okay, then I think I come to the end and I found some question. Okay.
Yeah, Prof. I guess we have questions from YouTube, but I guess the questions is already answered by your
really?
explanation.
Okay. Yes, that
It
would be
is
nice.
most of the basis sets use R321G, even though there are still 631G basis sets.
Yes.
So, Prof, what is the difference between basis sets 631G and 321G? I guess it is already answered.
Yes. Good. Very good question.
Yeah, very good. So I guess she is so hungry when you when you explain about the basis sets. So everyone, if there is any questions, so please you can ask directly, since we have our beloved lecturer here.
I hope more or less. Take your time to understand step by step. Encourage you, and we will have some example to understand more how to use the basis set, in which method, in which system. Yeah. Okay, then Mita and all, I thank you very much for your kind attention, and I will send the PowerPoint, okay, probably PDF, because the file is quite large. And
Sure,
to
thank you,
Mita, and please distribute to all interested people.
Sure, thank you very much, Prof.
Thank you,
Supa,
Professor
for
Supa.
the
Thank you. I
great
hope more or less,
explanation.
not completely, but anyway, I try to introduce to you. See you next time. Take
Thank
care.
you, Prof.
Yeah.
Thank you,
See you next
Professor.
time.
Thank you. Bye.
Have a good health.